Root 2 over 2, and what's sine of pi over 4? Root 2 over 2, right? So this right here, this complex number, written in its equivalent form, is e to the I what? Times pi over 4. E to the I times pi over 4 is that complex number, because this pi over 4 is the angle. Okay? You kind of following that? Sure? Let's see. Maybe. Let me give you another one. What about this number? What is that number written in its complex form? That would be 1 plus 0i, right? Right? 1 plus 0i. What is that rewritten with the e? E to the I times, what's the angle? What's the angle if you're right here? 0, right? But what's 0 times I? 0. What's e to the 0? 1. So it all makes sense, doesn't it? Yes? Okay. Here we go. Okay. What about this number? What's that number written in its complex form? 0 plus 1i, right? Okay. What's that written with the e? E to the I times pi over 2, because the angle here is pi over 2, right? Yes? Okay. If you're following this, great. If you're not, don't worry about it. We're going to move on in a minute. But here's the part that I think is just freaking mind-blowing, all right? What is I squared then? Well, that's just, well, what's I? That's this, right? That's I? So isn't that e to the I times pi over 2 squared, right? And what do you do here? You multiply, right? And isn't that just e to the I pi? So where are you then? That answer is where? What angle? What's that number? -1. I squared is -1.
It is impressive. We're just kind of thinking.
No, it is. I mean, I know it's impressive.
Through it, so.
And this is in mind. This is math. This is beautiful stuff right here. So in general, here's what we have. Now, I was on a unit circle here. This is a unit circle. But in general, if you take a number in the complex plane, a plus bi, and you measure the distance from here to here and call that r and call that theta, then this can be rewritten as r times e to the I theta. That is the general formulation of a complex number. Okay? And this, working with complex numbers this way, is so much easier than working with them this way. So if you want to square that, it's much easier to square this. Okay? One last thing. I promise I'm moving on. This is a good problem to give to your friends. You know your friends that are mathy friends? See if anyone's ever seen this before. What's I to the I? What's I to the I? What's I raised to the I? Right? That seems like a tough problem. So watch the way I'm going to do this. What's I over here? Here's I, right? What is that written in its e form? That is e to the I times pi over 2, right? That's this, raised to the I, but then what do you do when you have power to a power? Multiply. I times I would give you -1, so this is just e to the negative pi over 2, and that's a real number. So if you take the imaginary unit and raise it to the imaginary unit, you get the real number e to the negative pi over 2. That's pretty cool, huh? All right. Complex variables. That's the class where you get into that. Complex variables. More Maclaurin? Nah, let's do some Taylor.
Are you gonna send an email out like you did last time, just with like
Ideas, topics? Yeah, I'll have a pretty good little list of things to look at.
Okay.
Okay, find the Taylor series for f of x equals the natural log of x about 3. Taylor, not Maclaurin. Could we even do Maclaurin here? Yeah, not at 0. Maclaurin is 0, right? A is 0, and you can't plug 0 into that function. So you can't even do a Maclaurin series. There is no Maclaurin series for natural log of x. But you can do about any number other than 0, as long as it's not negative, right? Okay, so what are we going to need here?
Table.
A table with derivatives. Unfortunately, derivative natural log of x is not as nice as e to the x, right? All right, so here we go. The 0th derivative of this function at x, right? We're going to start at x. Let's go ahead and just do these as we go. So what is the 0th derivative? It's just natural log x. Okay, what is the first derivative of this function? 1 over x, right? Which is the same as x to the negative 1. I'm going to write it that way because I'm going to differentiate it again. So what is the second derivative of this function at x? Negative 1 over x squared, right? Negative x to the negative 2. You know, I probably would have gone from here to here, like from here to here, then there. But, you know. Okay, next one.
1 over x to the third.
It would be 2 x to the negative 3, which is 2 over x cubed, right? What would the next one be? Fourth derivative. So it'll be negative, right? And it'll be 2 times 3. But if you're starting to see, we're going to have to do this over and over. We don't want to turn that into a 6 because it's going to start to look more like a factorial because every time we're going to keep on increasing that number, right? 2, then 3, next one will be 4, then 5, then 6, right? So how about we leave this as negative 2 times 3 over x to the 4th. So that was the derivative. If I just take derivative of this, negative 3 comes out. I get negative 2 times 3, x to the negative 4, but I've dropped it down just to make it look like that. I need to continue this table, but I'm going to just continue it up here. What would the fifth derivative of this function be at x? Positive, right? Positive 2 times 3 times 4, x to the negative 5. So over x to the 5th. I think we might be able to come up with a formula for this. Because it's switching, isn't it? Isn't it like, it's like positive, negative, positive, negative, positive, negative, and that's dictated by which derivative we're on. See, in the previous problem, we had this cyclic nature, didn't we? But it was like every 4 was repeating. Here, it's every other 1. And we know how to make things change every other one. Let's just try it. What would the nth derivative at x be? All right.
Negative 1 raised to the n plus 1.
So I'm going to go with, let's alternate it first. We have at 0, we have what? 0 is a little bit weird, isn't it? It's natural log x, but it's positive, right? And then the next one is positive and then positive, then negative, right? So we don't alternate right away, but we start alternating here. So let's just focus our attention from here down for now, all right? Because this is the part that's alternating. Okay, so If we're at the first derivative, we are positive, right? Second negative, third positive, fourth negative. So to make that alternate that way, I need it to be -1 to the what? When I plug in 1 for the derivative, right, I need what? Positive? So what am I putting? n plus 1? Then times, now let's take care of the numerator, which has the factorial part in it. So I have 2 times 3, right? Here's 2 times 3 times 4, but what's the power? I mean, what's the derivative? It's 1 more than how far I want my factorial to go. So if this is n, what factorial do I want? N minus 1 factorial, right? 5, fifth derivative, you want 4 factorial. Fourth derivative, you want 3 factorial. So I'm going to go with n minus 1 factorial. Go with me? Over what? X to the n. Not a bad formula, is it? Now, that's not the formula we want to use, though, because we want to do it about 3. Right? So we still need to now look, can we come up with a formula for the nth derivative at 3, right? So that's easy, right? Because all that changes is that x gets replaced with 3. That's it. So we should be looking at -1 to the n plus 1 times n minus 1 factorial over 3 to the n. Yeah. All right, you ready to write the Taylor series out? This is not the Taylor series, right? This is just the piece that's going to help us write the Taylor series out.
I apologize. Where's that 3 to the n come from? Oh, never mind. Sorry. I got it.
You got it?
Yep.
Okay, so now, what we're trying to say is that our original function, natural log of x, should be able to be written as sum n equals 0 to infinity of the nth derivative at 3 over n factorial x minus 3 to the n. So that is what our Taylor series should look like, right? We're using 3 instead of 0 now, right? Now this top left corner of the formula right here, we generated a formula for it, didn't we? We generated a formula for it. But don't forget, we still have underneath that what? N factorial, okay? So our Taylor series is going to be, let's see if this works, sum n equals 0 to infinity of that thing, -1 to the n plus 1 times n minus 1 factorial over n factorial times 3 to the n times x minus a to the n. All right, let's see if that makes any sense. I took this right here, and I divided it by n factorial. That's this. You all agree? Okay, take that. If you were to divide it by n factorial, reciprocate, you'd be here. And then this x, oops, not x minus a, sorry about that, x minus 3 to the n. That's just this. Does this work? Remember I said we ignored the first one? We did, right? This only worked when n was 1, didn't it? It only worked when n was 1, not at 0, right? So how do we deal with that first piece? Yeah, we're just going to peel it off. Watch. Remember, we have that we need the first term is the function's value at 3, isn't it? So we have, this is not, okay, this is not it because of the 0. So what I'm going to do is this. natural log x equals natural log 3 plus sum n equals 1 to infinity of now negative 1 to the n plus 1 over n times 3 to the n times x minus 3 to the n. There we go. So I had to change this to start at 1 so that that formula would work. And I had to include that very first piece, the very first one, which was the function's value at 3. Right? Pardon? Yeah, see what I do with my factorials? I rewrote this factorial how? As n times n minus 1 factorial, and then like that. This is a little bit trickier, huh? I erased that table I had, which kind of throws things off a little bit, but.
So,
Yes.
with natural log of 3, you only to pull out that, you don't have to pull out like the whole thing.
Pull out what whole thing?
So like when you adding that as the first term and increasing n to starting at 1,
Mm-hmm.
you only have natural log of 3, you don't have to have like natural log of 3 over n factorial.
Mm-mm.
For that.
No, because all of that is going to be, well, what we need on our sum, right? This right here is going to be always our function's value at a, right? Because even with this piece here, it's going to be the 0. So that's going to be a 1, right? Everything else, I guess what you're asking me is you're doing the 0th derivative at 3 over 0 factorial x minus 3 to the 0. That would be the first piece, right? But this is a 1. That's a 1. And so it's just the function's value at 3.
We don't have 3 to the n.
Pardon?
We don't have a 3 to the n.
3 to the n. No, because this formula doesn't work for the first term. Had it worked for the first term, then we would have just started at 0. That was the whole problem. This formula only starts working after we took that first derivative. Does that help? Okay.
So anything, like, kind of like a general statement, like anything that we need to fill up, we'll take the function at about whatever number that is, and then add it to
The sum. And it's normally you're only going to have any issues like that at the 0th derivative. So it'll always, that first piece will always just be f of a. You know, I had a student a couple of semesters ago ask me a really good question. They're like, you know, great, these Taylor series are, you know, they're wonderful, but I mean, what's the deal? Because it's like in order to know what natural log of x is, I have to know what natural log of 3 is. Right? So what's the point? Like, how can you say that you have a new definition of a function when it relies on the value of the function itself? That's not the key to Taylor and Maclaurin. The key to Taylor and Maclaurin is that if you have any function, right, yes, you need to know a lot about that function. You need to know its value at a single point, don't you? You need to know its derivative at that point, its second derivative at that point, its third derivative at that point, its nth derivative at that point. You have to know a lot about what a function's doing at one point, okay? But from that, you can extrapolate what's happening everywhere else. And that's kind of like the big deal. And then we can convert a function into its Taylor series, and integration and differentiation then becomes easy, as the next example will illustrate. Okay, in your homework, you're going to have to come up with more Taylor and Maclaurin series. So you'll have a chance to work on that. It'll be fun. Promise, Michelle, it'll be fun. Okay, so now, evaluate correct to 4 decimal places. That's a definite integral, right? It's like an area under a curve, and you get to integrate that. All right, so we look at that and we go, all right, go back to our old techniques, right? Substitution, integration by parts, trig stuff, and there's nothing you have, all right? There's nothing you have. There's no way you can do this, all right? Just no way. So here's what we're going to do instead. We're going to look at our Maclaurin series for sine. What's our Maclaurin series for sine? Sum n equals 0 to infinity, -1 to the n plus 1 over 2n plus 1 factorial x to the 2n plus 1. That's our Maclaurin series for sine, right? So now what we do is we say, all right, that's if it was sine of x. But for us, it's sine of what? X cubed. So the Maclaurin series for sine of x cubed is just sum n equals 0 to infinity, -1 to the n plus 1 over 2n plus 1 factorial, but then x cubed to the 2n plus 1. Just replace x with x cubed, right? Which turns out to be sum n equals 0 to infinity, -1 to the n plus 1 over 2n plus 1 factorial, and then x to the 6n plus 3. Do you all agree with that? So in other words, this is the integral, the antiderivative of the sum n equals 0 to infinity of -1 to the n plus 1 over 2n plus 1 factorial times x to the 6n plus 3 dx. So do we know how to find the antiderivative of a power series? We did it last class, right? We did it last class. All of this right here, everyone, is our C sub n. So all we have to do is the power rule on this. That's it, just the power rule on that. So what is the antiderivative of that going to be? Sum n equals 0 to infinity, -1 to the n plus 1. The C sub n does not change. 2n plus 1 factorial, and then what? X to what power? 6n plus 4. All we're doing is adding 1 to the power. And then out front, you have to do 1 over 6n plus 4. So all I'm doing is power rule on this right here. Right? Like if that was x to the 5th, you would put 1/6 x to the 6th, right? We're just adding 1 to the power. Do you all agree? That's the antiderivative, but we want to evaluate this antiderivative from 0 to 1, right? 0 to 1. I'm going to go to the next line. So I'm not ready to evaluate yet. I'm going to write this power series out. If n is 0, where are we? Let's see, if n is 0. Negative 1 over, n is 0, 1 factorial times 1/4 x to the what? 4. Okay. Plus, what would be the next part of this series? If n is 1. We get a plus here. We get 3 factorial. And then times 1 over, what, 10? X to the 10th. Okay. Plus, now what's n? 2. So that would give us a minus, wouldn't it? I guess I should have put that minus. 2 down here. 5. So 1 over 5 factorial times a 2 right here, 1/16, and then x to the 16th plus dot, 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 right? This keeps going. I could keep going with this, but I want to evaluate that from 0 and 1, right? 0 to 1. Okay, let's plug in 1. Plug in 0 first. Yeah, I mean, that one's easy. We all understand when we plug 0 in, everything's gone. So all we got to do is figure out what happens when you plug in 1. When you plug in 1, all the x's to those powers are nice, aren't they? There's 1s. So this is really negative 1/4 plus, let's see, what is 3 factorial? 6. So this is 1/60th. Okay, minus, all right, what's 5 factorial? Might need a calculator for this one. Because then you have to hit it with 16. 120 times 16. Is it 600? I believe you. Oh, no, it's not, but it's okay.
Oh, smart. I guess not.
I believe it. Well, you know, arithmetic is arithmetic, right? Doesn't make you smart. Okay, next.
Oh, man, I was
You see what I'm saying?
saying?
Okay? Yes? Got it? So now, let's just look at this as a decimal. We're stopping right here. Let's just see what happens. It's like 0.25, negative 0.25, right, plus 1/60th, and then minus 1 over 1920. So I'm getting approximately right now negative 0.233854. Okay, it goes on some more. What would our next term be in our series? It's not written up here, but it should be plus, right? 1 over 7 factorial. What was it? 6n plus 4. So where would we be at? 3? 3. What is it? 20? 21? Wait a minute. Hold on. I'm way off here. 1 over, it's going up by 22? 22, and then x to the 22. Yeah, that's it, I believe. That would be our next piece, right? And then we plug 1 into that. Let's see what we would get.
Is that a safe assumption to make?
What?
I got those numbers because I just looked at the pattern. But
Yeah, you can start looking at the pattern.
It doesn't change the first 4 decimals.
It doesn't change? Okay, so if you add this piece to this, the first 4 decimals don't change? Okay, so you can just check it yourself. You add this piece in with a 1 right here. This first 4 decimals don't change, which means we've gone far enough. And how many terms did it take in our power series? Just like 2 or 3, we're there, right? How many do we have if we need to be more accurate? How many more do we have to mess with? Infinitely many, right? So that's what I'm saying. You can be as accurate as you ever want. I mean, look at that. That is an integral that cannot be done by hand, right? You cannot get an answer, but you can still do definite integrals. You can still figure out areas, volumes, all that stuff with the power series. Very cool, right? Now, formula sheets. Can I borrow yours? So on our website in Canvas, there is this sheet here. It's printed sideways, and it has the common Maclaurin series. So it has e to the x, sine x, cosine x, arctan x, natural log. These you're allowed to have on your formula sheet. If I ask you to do an integral like this on the test, on the final, if I ask you to evaluate an integral like this, I expect for you to go to that sheet, all right? I do not expect you to have to first find the Maclaurin series of this on your own. You don't have to do that, okay? But I will tell you in the problem, evaluate this integral using your Maclaurin series table, all right?
You are
Right?
rock star, man.
Well, I mean, that's common. In like as you move on, if you need to ever do integrals, you always want to just go to the Maclaurin series.
Well, we didn't know.
Yeah.
We all thought we were going to have to do all that.
Well, no, there will be those. There'll be separate problems. So there will be other problems where I say, here's a function, find its Maclaurin series. And there I expect you to do the table or the list and stuff. Okay? I don't think I have time. I do have time. Yes?
Do you have an idea like how many questions roughly?
I don't. No, it's not that long.
A bunch of integrals, you know.
Let me see.
47 integrals and 3 McLaren and Taylor. Sounds about right.
Let me see if this thing works. I'm going to show y'all something here. I haven't made the test, so I can't answer that. Mostly chapter 8. Hold on a second. Why is All right, so this is a little premature to be showing this to you. I know y'all want to get out of here. So can I answer your question later? Because I don't have that information yet. Okay. I'm not sure how this is going to work out. All right, can we kill the lights real quick? I like to show this little video here. Okay, what I don't know is how this audio is going to sound.
Use our imagination. Let's read the line.
You kind of need to hear the audio on this, but let me see what the audio sounds like. Just on the lap. Hold on. There's an audio thing here. Can you turn that on real quick? Just a couple. More. I think that's it. Oh, I hear speakers. Yeah, okay, that'll work. Okay, so you can kill the lights. All right, so we have a few minutes, right? So this is an old video. I don't know where it was shot, but just want you to watch this. See if you can hear, and I'll translate in a second, but okay, here we go. Can you see?
How you seems that you are not happy.
Seems that you're not happy.
You are not happy with the series.
You're not happy with the
How you
series.
multiply the series? But let's see now.
Seems like you're not happy. You're not happy with the series, multiplying the series.
Do these subtitles suck?
Some other example. What
Are
I
there
can do-
subtitles on?
No,
Oh,
little
yeah,
comment.
let me.
I guess not.
Because if their work happens, they can go up.
Yeah,
Well, then he is a horrible teacher. No subtitles on the video.
hold on.
Yeah.
Oh, goodness.
Y'all just watch and listen.
Multiply.
You can't hear what the student's asking, so I'll translate it.
Yeah.
Can I ask you a question? So on there, how did you get from the first line to the second line was the question. All right?
You multiply.
You multiply. That's what he said. Can you show it? The student's saying, can you show us exactly how?
Not exactly how, let's see.
We multiply by 1. 7 times what equals 1.
Okay.
5 times 1 equals 7.
From here to here.
Yes.
Or you can divide 1.
Okay, so he goes from here to here. And they said, yes. He said, did y'all hear what he said? You divide 1.
No, that is Can you do it manually? It doesn't work.
Can you all hear what the student's saying? You do it manually, it doesn't work?
Doesn't make any sense.
Doesn't make any sense.
Okay, let's go further.
Why are you ignoring my question? That
No, you are doing this.
You don't answer anybody's questions.
Okay, so. Okay, so the student did not know how to go from this line to this line. He asked the question of, how do you do it? What did the teacher say? You divide 1. Okay? Is it the professor? I'm saying this is a great professor. I'm not saying that. But is it the professor's fault that this student doesn't know how to divide an infinite series into 1? Like, how do you divide 1 by an infinite series? Is it the professor's fault? This is not a Cal 2 class. This is beyond Cal 2. So a student should be able to manipulate power series without any issues. The fact that the student is asking them and telling them it doesn't work. Trust me, when the professor's sitting there with that piece of paper in front of him, like that stuff's correct. Like, it's been worked out before class. You know what I'm saying? So I think the professor could have done a better job in terms of like, hey, you know, if you need to go back and review multiplication, division of power series, that's where, you know, that's what's happening. But I really think this professor thinks that the student is just messing with them. You know, I don't know. We weren't there the whole semester. What I'm getting at, next class, we're going to multiply and divide power series. All right? And that's exactly what this step is. You're taking the number 1 and dividing it by that entire infinite series, which goes on forever. And I did a follow-up video to this. It's somewhere on my YouTube channel where I actually show the division and show that it goes from this line to this line. It's not incorrect. And a lot of the comments you'll read on this is like, this is why higher education sucks. I'm not throwing my money away for this crap. Then you'll see other people who are like, it's just simple arithmetic. Why don't you just like learn, like, why don't you be the whatever engineer you say you want to be instead of being condescending? You know, if you're ever in a class where you don't understand line 1 to line 2, that's your job to go figure that out. Okay? The professor's there to deliver all the other information for the course. That's like that's a little ancillary topic within the bigger topic, right? If you're struggling with that, you go get that fixed. Does that make sense? So next class we will go through, I don't think I'll do that one. It's not any harder or easier, but it's just, the arithmetic is, well, it's long division. I mean, you know how much you love long division, right? It's long division with an infinite series, yeah. It's not that bad, it's just you'd have to follow patterns and, okay. I will come back next time, have a little more information about the final for you, and bonuses will at some point be put in.
You want the homework packet on the final day of the final?
Yeah, day of the final. Mostly chapter 8. Mostly chapter 8.